In the beginning, there was nothing. Even calling the time before the Big Bang nothing is an overstatement. It was not dark, nor was it light, for light itself had not yet been created. All that was, or could be, simply was not there. 13.7 billion years ago, the universe exploded, creating the fundamental building blocks of the universe. At first, the universe was as small as an atom, with temperatures so tremendously hot that matter and energy were interchangeable. But then the universe went through a period called inflation. Inflation was an extremely short, but also incredibly rapid period, between 10 to the negative 35 seconds and 10 to the negative 32 seconds after the Big Bang, where the size of the universe increased from the size of an atom to around the size of a galaxy. This early universe existed as a plasma, without much structure or complexity, until around 380,000 years after the Big Bang, when the universe cooled down to around 4,000 degrees Kelvin, which was cool enough for protons to form with electrons to create the first neutral atoms. These first atoms were composed entirely of hydrogen and helium, with a slight smattering of lithium. It is from these elements that even greater complexity was able to arise. After these particles were created, the universe consisted of giant clouds of hydrogen and helium gas. Eventually, electrostatic attraction between atoms in these clouds allowed them to start to clump together, and as these clumps grew, so did their gravitational field, creating the first protostars. Over time, these protostars were able to gather huge amounts of hydrogen and helium gas, and as this gas was condensed under the force of gravity, it started to heat up, getting hotter and hotter, until the center of these protostars reached 10 million degrees Kelvin, the crucial temperature needed for nuclear fusion reactions to take place. Once this happened, the compressive force of gravity was able to be countered by the expansion of the superhot gases inside of these stars, creating stable, main-sequence stars that were able to achieve hydrostatic equilibrium, vastly increasing the complexity of the universe from clouds of dust to massive shining torches of plasma. This early universe contained lots of stars, but not much else. All of the other heavier elements besides hydrogen and helium were still brewing inside of massive stars, much more massive than our own sun. The cores of these massive stars soon run out of hydrogen to fuse into helium, and when this happens, fusion ends in the core, and these stars start to collapse. But once the temperature of the core rises to 100 million degrees Kelvin, helium is able to be fused in beryllium, which then fuses with another helium atom to form carbon. After this, stars create nitrogen and oxygen, all the way up to iron. But once a star tries to fuse iron, things get messy. As usual, a star will nonchalantly start to compress under the force of gravity to try and raise the temperatures in the core hot enough to fuse iron. But when iron fuses to create new elements, it results in a net loss of energy, not a net gain. So the star keeps collapsing, until the collapsing material rebounds off of the superdense core and creates a humongous explosion. These explosions are called supernovae, and in the massive temperatures and pressures that supernovae create, even more massive elements are able to be formed. Gold, lead, uranium, silver, all of these elements were forged in the explosive death of massive stars and then spread throughout space by their death throes, which helped to create new forms of complexity and laid the groundwork for the creation of the solar system. Around 4.56 billion years ago, in a rather nondescript portion of the Milky Way galaxy, a star was born from the leftover gas and dust to some long-forgotten star. A large disk of gas and dust, called a protoplanetary disk, swirled around this embryonic star. Soon this star reached the Goldilocks condition of 10 million degrees Kelvin, and switched on in a brilliant display of nuclear fusion. The solar winds that came streaming from the star pushed back the lighter hydrogen and helium gas, allowing heavier elements to congregate near the star. From this protoplanetary disk, small planetesimals or embryonic planets were able to form. These small planetesimals had very unstable orbits and would collide with one another while accreting material. This early solar system was our solar system. Appropriately, this early period of the solar system was called the Hadean epoch. One of these little planetesimals would eventually form the Earth. This early Earth did not have enough mass to hold on to an atmosphere, but the Earth was also busily accreting material. Some of this material was much more massive than others. Sometime after the early Earth formed, another planetesimal, around the size of Mars, crashed into the Earth, cracking off the light, silicate-rich outer layers of the Earth, which would swirl around the Earth until it eventually formed the Moon. As the Earth cooled, the metallic, heavier elements settled into the core of the planet, and since the impact of the Mars-sized body with the Earth also imparted its metallic core, the Earth formed with a very large metallic core. This large core then created Earth's magnetic field. With the addition of a stabilizing moon and a powerful magnetic field, the conditions on Earth were just right for the emergence of even greater complexity on this amazing new world, life and the eventual rise of civilization.